Okay, just a quick review. We've already talked about esters in the end of unit 2, and an amide in some ways is similar to an ester. Instead, it's a combination of an acid and an amine. Okay, so let's get into this. Now, these are really important biological molecules, as well as esters.
Professor, did you by any chance upload this
Yes.
slides?
Yeah. Yeah, that's what I said in the very, very beginning. If you go to, let me verify that.
I just found it. Thank you.
Okay. Okay, so amines and amides are extremely important molecules biologically. Speaking, an amide basically is how a protein is put together with amino acids. Um, Other molecules like alkaloids, such as morphine, they're just, nitrogen is very, very prolific biochemically, as well as oxygen in the formation of esters. Now, an amine comes from ammonia. Someone have a question? Now, one of the things about an amine, it's based on nitrogen. Nitrogen has a single unpaired, an unbonded pair of electrons. Just as oxygen is two. And that forms a lot of the chemistry. And the chemistry will come in terms of a special bond that I'm going to talk about in a little while called a coordinate covalent bond. And that electron pair on both the oxygen and the nitrogen comes into play for that type of special covalent bond. Okay, like alcohols, we're going to have primary, secondary, and tertiary amines, just like we have primary, secondary, tertiary alcohols. It has to do with the number of hydrogens present. Okay, in terms of primary, there are 2, secondary 1, tertiary, there are none. Okay, common names for amines. All they do is they name what's hanging off of the nitrogen in alphabetical order. So in this case, we have an ethyl and a methyl, so it's ethyl methylamine, dimethylamine, methylamine. And that's frequently used. Now, yeah, go ahead.
So, to like identify amines, you would like look for the NH. Is that what you would look for? Like how alcohols have OH, the stuff like that. That's how you would just like see if it's a amine, if it has the NH. Or do we?
Yes, except the amino group can be used as a branch or a functional group as well, which I'm going to get to in the next slide. But yeah, that's how you look for it. You'd go, what's hanging off of that?
Okay, just wanted to make sure. Thank you.
Okay, the IUPAC name for this is basically treated as a branch. So backbone, 3-carbon backbone, and at position number 2 is an amino group. So it's 2-amino propane. And frequently it's written this way, and also some people put a dash between the amino and the propane. In this naming, the alcohol is taking precedence in terms of the name of this over the bromo and the amino group. So the basic backbone here is going to be an alcohol with an amino branch and a bromo branch. Okay. Now, one thing that's a little different than naming alcohols is that you can have stuff attached to the nitrogen. So if we look at, that's this over here. If we look at this guy here, it's basically a pentane with an amino side chain on carbon number 2. So it's 5 carbons, 5-carbon backbone, and the penta. If you count from here, it'll be the lowest. So it's 2-pentaamine. Here we've got a 1, 2, 3, 4-carbon amine, a carbon number 1, and a branch on carbon number 3. Say again. Someone have a question? Okay, now this is trickier than an alcohol, because if we have some kind of a group hanging off of the nitrogen, that's where this uppercase italicized N is. So it's a 1, 2, 3, 4. Position number 2 is where the amine structure is, but we have a methyl group off of that nitrogen. So that's what this is. That N-methyl refers to that. And say we had that. We had 2 methyl groups hang off of the nitrogen, and it would be let's see. Okay. And those could, and say this was a, instead of 2 methyl groups, say it was an ethyl and a methyl, then it would be N and ethyl, methyl, to amine. Now we start naming amides, that's going to come into play is again. So whenever we have something other than hydrogens on the nitrogen group, then you have to spell it out using these N's. Okay, does that make sense?
Yeah, it does.
Okay, as far as aromatic amines go, this is the most simple one. And instead of calling it aminobenzene, they call it aniline. So everything's going to be based upon the aniline, not the benzene part of the aniline. So here we've got a branch from carbon number 2. And we have a methyl group hanging off the nitrogen. So let me see. This part is that. And then this part is this. As far as intermolecular forces go, because the oxygen has 2 lone pairs instead of just 1, its polarity is maybe oxygen polarity, because of the 2 lone pairs, makes it more polar than the 1 lone pair on the nitrogen. Hence, the boiling point for alcohols will be higher than the boiling point for nitrogen base. So if we look at a graph of, let's say, boiling point or surface tension or melting point, we would have our normal and then esters would fall in with this guy, and amides would fall in there as well. So acids are the king in terms of, now this is not an ester now, it's an acid. So it's got a COOH. And then up here, and one more, would be something ionic, like the salts of acids. We haven't talked about ammonium salts, but we'll talk about it in a minute. So the ionic ones are particularly polar. And hence they would have the highest boiling point. And then this would be increasing molar mass, increasing size, basically. Okay, so this is important because frequently a question will be asked, I'll give you some compounds and which has the highest boiling point. So you need to keep this order in mind. The good old alkanes, alkenes, those are the least polar. The ionic ones are the most polar. Okay. Nitrogen compounds generally are soluble in water because of the okay, so this nitrogen, just like the oxygen, was partially negative, making these hydrogens partially positive. And since this is partially negative, that's where the attraction comes in. And same with, oops, same with water. Okay. So the hydrogens on water are partially positive. That's what's attracted to this partially negative nitrogen lone pair. And the lone pairs on the water would be attracted to the partially positive hydrogens on the amine. And the more of the so as far as polarity goes, okay, when you start getting these alkaline groups coming off of the nitrogen, that softens the polarity. If you just have hydrogens like pure ammonia, that has the least amount of softening. And that's what these boiling points reflect. So here, for example, difference between these two, this has got every single point of the nitrogen's got some kind of an alkyl group on it. You look at these have got methyls, these have ethyls, and look at the difference between the two. Okay, this is a lot more mass. There's two things going on here. Mass and polarity. So the difference between these two is mass. And again, the reason why we're getting that hydrogen bonding is because of the partial positive and partial negative charges on that nitrogen and oxygen molecules. Now, amines can have a very unpleasant odor, just as sulfur compounds can have an unpleasant odor. And it's for the same reason, actually. For example, if you look at this 4-carbon double amino group, in this 5-carbon double amino group, there are very, very, very unpleasant smells. In fact, they even named them. The common name is putrescine and cadaverine. This future, both these come off of decaying animals, so they can be really stinky. Okay, now this is really important. If we have a nitrogen compound, and or these can all be, in fact, let's just do this one of them. What can happen is that can bond with that lone pair on the nitrogen. When that happens, this comes across oops. This ends up coming across as the hydrogen only without its electron comes over and does a very special kind of covalent bond where the hydrogen coming over has no electrons. So to achieve its full shell, it bonds with the electron pair on the nitrogen. And that's called a coordinate covalent bond. Because the hydrogen comes over with no electrons, it leaves an extra electron on the original water group. And because the hydrogen came over with a deficiency of electrons, the overall group over here on the nitrogen side ends up being a positive cation. And this group here is called ammonium. So there's ammonia and ammonium. The yum is the ion. So one of the definitions of a base is a hydroxyl ion dissociates. So if there's an OH present and it dissociates, it's considered a base. So an ammonia compound or an amine in water will form this base because the OH comes from the water losing one of its H's, and it leaves without its electrons. I should say electron, one electron. Okay. The two-way street also. So whenever the amine is, it's going to grab hold of one of these hydrogens and bring it over. So if it's a methyl amine, it'll be methyl ammonium ion. Now, additionally, definition of an acid. An H plus disassociates. So if an amine is in the presence of an acid, the fact that it's an acid, it exists like this. So that H plus now is going to do the same thing. And the amine salt is the ammonium plus the anion part of the acid. Okay. So just in water, it's methyl ammonium ion. Once it's in an acid solution, then you have to take on the anion part of the acid as far as the name goes, and that goes there. So if we have a weak acid, let's say a weak base, looking at the ionic character, and let's say pH less than 7 in an acidic environment, there's no change. A weak base in pH less than 7, we end up with the ammonium salt. Okay, so this is non okay, so if we have a weak acid and a weak base, and the pH is greater than 7, we end up with the acid salt, and there's no reaction. So here, let me see. Okay, so in acidic conditions, an acid is going to have no change. A base is going to be, the acid is going to pull so let me rephrase this. Okay, in a acidic condition, this would be acidic condition. There's going to be no change on the acid. However, with the base, what's going to happen is the hydrogen from the acid adds to the nitrogen. In basic conditions, the acid is going to be deprotonated by the OH, forming water, which leaves the acid salt left over. And the base, nothing happens because there's no H plus to add to the nitrogen. Okay. This is a frequent question on worksheets and tests. Okay. Are there any questions about this? Okay. Okay, so we have here we have an acidic environment. So that H is coming off and adding to the nitrogen. And this is the salt left over. So it's ethyl ammonium acetate, or ethanoate. Okay, so naming these ammonium salts, or amine salts. All we're doing is we are taking the nitrogen, which is the ammonium part, we're taking the forming ionic name for the anion. And then the front part of this is going to be in alphabetical order. What's attached to the nitrogen? Next is both of these together. Forms ammonium. That's the anion name. Now, this is frequently done when chemists are trying to synthesize drugs that are more motile in the blood, since the blood is mostly water. So you've got to have some kind of polarity to the molecule before it can be moved around in the blood. So what they'll do is they'll frequently have some kind of an acid that ends up going over here. So you end up with an ionic compound. Now, this isn't all that insoluble because we have alcohol groups here, and we have an ether here. Okay, these all are polar functional groups, particularly the two hydroxyl groups. So this has some polarity, excuse me, this has some solubility in water. This is just more soluble. One take-home question I gave I used to get shots, vitamin B12 shots when I was little for asthma. And it looked more like this. And because it looked like this, it was very insoluble in my blood. So when they injected it in my large muscle in my butt, it took hours to disperse. So I could not walk for hours. And it was very uncomfortable. I remember my dad taking me and he'd buy me little things at the 5 and 10 cent stores just to kind of get my mind off of the fact that I couldn't walk. And one of the questions on the take-home test was I gave him the structure of vitamin B12, which is kind of wildly complicated. And I just said, make this more soluble in blood. So what they had to do, they had to analyze the functional groups and modify them to be more soluble in water or more ionic. Now, so this would be the ammonium salt. And then this guy grabs at H plus and forms water. And what's left over is the sodium chloride. These form your water. So this is what I talked about a couple slides back. Only I added in the acid part. Okay, so as you remember on the tests, I had an ester. I asked you 3 ways to form that ester. Okay, so it's the acid plus alcohol, the acid plus the anhydride, and the acid plus the acid. Oops. The acid chloride plus the alcohol. Now, an amide acts like a weak alcohol. So that means, and when I have, remember, this is yield. The acid chloride gives the best yield. The acid gives the least yield. Okay, with forming an amide, the acid plus the amine. So down here, we're going to have so the reaction with the amine with carboxylic acid does not produce the amide. So we're going to need the acid chloride, most yield. Least yield. So it's just like with the esters, except what's missing is the acid plus the amine. So here we have the acid anhydride. Here's the amine. So anhydrades always yield an acid when they come apart, bond. So here's the acid anhydride. Here's the amine. So this is going to be the amine part. Just like we always list the alcohol part when we name it ester first. And this comes from the acid. So it's N-methylbenzamide. Okay, so this is the acid chloride. The amine. And notice we have methyl groups hanging off that nitrogen. So that's what's represented on the N dimethyl. So, meaning the presence of an acid forms the salt. This would be the ammonium salt. In the presence of water, the amine will grab hold of the hydrogen from the water, leaving a a hydroxyl ion. That's why the amine is considered a base. In an acid chloride, we're going to form the amide, leaving the residual acid part left over. Same with the anhydride. Now, because this has only okay, then this reaction actually needs an amine to go with this. You can't form an amide without an amine plus some kind of an acid. In this reaction, because as I said earlier, the acid plus the amine does not give an amide, it gives the salt. So this reaction, the way it's written, doesn't work. It yields, I don't know why they give this as an example. Okay, so we have an amide here. Okay, just like with esters, the carbonyl is the acid side, the N is the amine side. And here we've got methyl groups hanging off of the nitrogen, so that's denoted by the NN. And we have one methyl group here. Okay, there is some hydrogen bonding. And then the same thing applies with waters. Okay, just as with esters, we can hydrolyze the ester, meaning taking it apart into its original acid and alcohol. Same with amides. We can hydrolyze it, adding water. We end up breaking the amide bond here. This guy here. We end up going to the acid side, the amine side, acid, amine. As I said before, proteins are amide bonds. So if this is a protein, you end up with amino acids. And the enzyme that does that is called protease. So proteases catalyze the hydrolysis of amines. And that requires a low pH. Usually around 2. What your stomach acid is. Now, as that one I went before, when you have an so when you have a pH less than 7, when an amide breaks up, you end up with a carboxylic acid and with salt. Ammonium salt. In a basic environment, what you end up with is salt the acid salt and the non-ionic amine. So we have acetamide. So again, this is the acid part, amine part. And we have pH less than 7. And when the acid breaks off of the amide, the H is going to go on to the acid right here. And actually, the OH goes there. And then the H goes there. We end up with an ammonium salt. So in basic environment where pH is greater than 7, what's going to happen is the OH here is going to grab the hydrogen off the acid, forming the acid salt plus the amine. Again, now there are thousands of important amides in medicine. Thousands. There, if you look at this amide, 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 amide. And you need to be able to recognize those NCO, C double bond O linkages. Because to make that, you would then put together an acid chloride for this piece and the ammonia part for that piece. amide, 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 all over the place. And this is various forms of penicillin. So depending on these functional groups, will change the characteristics of that penicillin and how it interacts with bacteria. Okay. So this unit is very similar to the acid ester unit. This is the acid amine unit. Very similar characteristics, not the same quite, but similar in terms of the way the acid and the amine work together, the acid and the alcohol work together. So what I want to cover on Wednesday is going to be the biochemical part of this, which would be looking at proteins and amino acids and zwitter ions, a whole bunch of stuff. Okay. That's what I wanted to. Are there any questions about? Let's see. We have a chat question here. Okay. Nora, I see your message there. Yes, I'll add worksheets in a few minutes when we conclude this lecture. I'll have them in the same place on files. Okay, so are there any general questions? I'm still working on grading the tests. I wanted to get them back to you sooner, but I didn't. And I apologize for that. I will really focus on it. It bugs me that I'm not getting them back to you in a more timely manner. So again, I'm sorry. Okay, are there any general questions? Now our labs this week are going to be interesting. We're going to be in the instrument room running IR analysis on your on three things: your synthesized aspirin, which should be dry by now, and then you're going to analyze salicylic acid, which is one of the precursors to aspirin, and then you can also analyze the commercial aspirin, all three of those. And then you can compare the IRs, and you should be able to come up with some similarities and differences between yours and the salicylic acid, between yours and the commercial aspirin. That's one of the things we're doing today. The other thing we're going to be doing is doing a phenol test, which is a test for salicylic acid, which is a phenol. And if it's present, that means you have unreacted salicylic acid in your product. We're also going to be looking at melting points. So you need to take the melting point of aspirin, commercial aspirin, salicylic acid, and your product. So those are the three things we're going to be doing today as far as the actual lab activity. And then filling in anything on section 3 from the first part of the lab. Okay? It shouldn't take very long. I'm just saying though that there's a lot of parts to it, but the parts go pretty fast. Okay. So are there any other?
I just have a quick question.
Yeah.
For last week's lab that we did, since we weren't able to like fill it out completely, are we going to be uploading that one on this Wednesday?
No.
No, is it going to be the following Wednesday?
Yeah.
Oh,
Think of this last week's lab and this week's lab as one lab.
okay, but we still need to do the lab write up for this one, right?
I mean the pre-lab?
Yeah, like the pre-lab and everything.
No. It really isn't pre-lab, because you've already made this stuff. That's where the pre-lab, no pre-lab. You've already done the pre-lab, you get a smiley face.
Okay, because there was like a pre-lab for this one, so that's why I was kind of like confused.
Well, I mean, they're pre-lab questions, but there really isn't a classic pre-lab. Does
Okay, okay, thank you.
that make sense?
Yeah.
In fact, I'm just talking to the department chairman. Just before I started,
So should we just do? Can you hear me?
just do what?
So should we just do the questions then and then not do like all the other stuff?
Yeah,
For the-
you mean like the procedure and all that stuff?
Yeah, like just the questions, no procedure, no materials, like all that stuff, just the questions.
Yeah.
Okay, perfect.
Because the procedure, you're going to be using the IR spectrophotometer, which is horrendously easy. You just put the sample in this little spot after you clean it, and then run it. 2 steps. Well, and the third step is to clean it when you're done. With acetone. That's it. It's super easy. And the melting point device, you put it in your little capillary tube. I'm going to show you how to do all this stuff. You put in this little capillary tube, and then you watch at what temperature it melts. So, it goes really fast. And it's really easy. It's really, and these 2 procedures are done if you had taken OChem, the STEM track, the year-long class, you'd be doing these every single time you made something. Every single. So you'd end up doing like this, what we're doing today, 40 or 50 times by the time you're all done with OChem. It's a very, very routine. And there's other instruments you'd be using. You're using the NMR. You might be using, well, I don't know. I don't know what they do in this OChem class, but frequently they'll use a magnetic, nuclear magnetic resonance, or an NMR. They'd be using a GC spectrophotometer with mass spec analysis. I mean, there's a lot of instrumentation, but I don't know what this department uses for their OChem. I know they use IR for sure. Every OChem class in the country uses IR, and melting point. Those 2 for sure. And everything else depends on the department's instrumentation, whether it's, they have it and it's working or not. Okay. Anything else? Okay, so why don't we end this? And I'll be putting worksheets up like right now in Canvas.